Okay, so last time we discussed about hydration curves, and today we're going to focus on the buffer region, the point at which the pH do not change that much at all. Okay, so here they are. So for for the buffer region to happen, you should have a mixture of acid and its conjugate base, or a base plus its conjugate acid. Okay, you have to have one of the following for you to have a buffer region. Okay, so what do we know about buffer region? Um, it is a region or a solution that resists changes that much when you add um, acids or bases. Okay, so the idea is that the pH of the solution do not change that much. Okay, so that's one thing that's special in buffer region, and that's something that is quite wonderful because in our body we have a lot of buffer systems. In our blood, we have carbonate buffers. Um, in our cellular matrix, we also have carbonate buffers and hydrogen phosphate buffers whatsoever. So buffer regions are everywhere, especially in the body, because imagine yourself just um, drinking some sour foods, then you die. Okay, that doesn't happen because our body is packed with buffer solutions. That means even you take in acids, your body's pH do not really change that much. Okay, so you're safe. Okay, so anyway, that's more on biochemistry. So let's go back to analytical chemistry. Okay, so the question here is how are we going to compute for the pH in a buffer region? Okay, so you can use your ice table. However, I will be presenting to you a simplified version of that process. We call that the Henderson-Hasselbalch equation. Okay, so this equation is just a derived form from the ice table that we already discussed beforehand. Okay, so the good thing about Henderson-Hasselbalch equation is that you don't have to do ice table. Instead, you're just going to get the negative logarithm of your acid Ka plus the logarithm of the concentration of the conjugate base over the acid concentration. And these two are very easy to solve for because they are already given in your questionnaire or in a problem. Okay, so these two are very easy to solve. So using the Henderson-Hasselbalch equation, we do not have to do ice table process. We're just going to plug in this and this in our equation to get the pH. So the counterpart for bases is this. Oh, by the way, yeah, so this is the counterpart equation for bases. You still have this equation and this part. Okay, the concentration of base and the conjugate acid. So the two concentration are very easy to solve. Okay, so let's have one example. So let's do that here. So let's have here a buffer solution was made using 10 grams of sodium acetate and 200 ml of 1 molar acetic acid. Assuming the change in volume when the sodium acetate is not significant. Okay, so I have a typographical error here. The sodium acetate is added. No, is added. Okay, so when the sodium acetate acid is not significant, okay, estimate the pH of the acetic acid sodium acetate buffer. Okay, so we're asked what is the pH of the buffer solution that we have here. What is the pH of this solution? Okay, of course we're going to use the Henderson-Hasselbalch equation. So since this is an acid, because we have acid, okay, so we're going to use the acid form. So that's pH equals pKa plus logarithm of the conjugate base over the acid concentration. Okay, so after writing that, we're going to compute for the value of this, and this. Okay, so let's write them on the side. So for pKa, we can solve this from the Ka. Okay, so what is the equation for pKa? That is just the negative log of Ka. So this is the negative log of 1.7 times 10 raised to negative 5. And that is equal to 4.77. Okay, so the pKa is 4.77. How about the concentration of acid? Okay, so for acid, the concentration is already given. We have 1 molar of acetic acid here. So we're going to write there acid 1.0 molar. How about the conjugate base? Okay, so how are we able to obtain the conjugate base? What is this, the reaction? Okay, so the reaction is that you have your acetic acid, CH3COOH. This will dissociate into protons and acetate ion. Okay, so in the problem, it tells that the acetate, this acetate ions came from sodium acetate. Okay, so all our acetate ions originated from the sodium acetate solution. So in order for us to get the concentration of this, we have to solve for the concentration of sodium acetate in our solution. So we're going to do that to solve for the concentration of the acetate or the conjugate base in molarity. That is the grams of sodium acetate over its molar mass times the volume of the solution of the sodium acetate solution in liters. Okay, so to solve for that, is the concentration of acetate equals 10 grams divided by sodium acetate. I do not have a molar mass given here, so allow me to use my periodic table. So sodium is 22.99, CH3 COO. So the molar mass for the acetate is 82.034 grams per mole times the volume of the acetate solution, which is 200 ml. So I'm going to convert that into liters. Okay, so that's 0.2 liters. So the concentration of acetate is 10 divided by 82.034 times 0.2. So that's 0.6095. We'll round that off to 0.610 molar. Okay, so having the concentration of conjugate base computed, and we have the concentration of the acid, we can now solve for the pH of the buffer solution. So how are we going to do that? We'll use the Henderson-Hasselbalch equation. So that means the pH of the solution is pH equals the pKa plus the logarithm, the concentration of the conjugate base over the acid. Then we're going to plug in all the concentrations. So we'll have pH equals 4.77 plus log of conjugate base 0.610 molar. The acid is 1.0 molar. So solving for that, the molarity cancels out anyway. So the pH of solution is 4.56. Okay, so this pH of the solution is 4.56. So that's how you solve for the pH of a buffer solution. So very easy. Okay, so we'll try the next problem. Okay, so let's try to solve this. Calculate the ratio of amount of ammonium chloride to ammonia that is required to make a buffer solution with a pH of 9. The Ka for ammonium ion is 5.6 times 10 raised to negative 10. Okay, so what we're going to do here is to make a buffer solution with that condition. Okay, oopsie. So we're going to calculate the ratio. Okay, so we can do the equation for acids. That's pH equals pKa plus log of the conjugate base over the acid. Or we can do this in terms of the base. The base equation for Henderson-Hasselbalch is pH equals pKa plus log of base over the conjugate acid. Okay, so we have two equations. Which of the two are we going to use anyway? So let's look at the problem. So we are asked to look for the ratio of ammonium chloride and ammonia. Okay, so what do we know about the two? They are base. Okay, so we're going to use the base equation. Okay, however, let's try to check the problem. Okay, ammonium chloride and NH3. What's the relationship between the two? Ammonia is the base, and ammonium chloride is the conjugate acid. Okay, so if we are going to solve for this ratio, we are actually obtaining the ratio of ammonia to ammonium chloride. However, the problem requires us to solve for the ammonium chloride to ammonia. We are asked to solve for the ratio of the ammonium chloride to ammonia. Okay, so that means after solving the problem, we're just going to get the reciprocal of our answer. Okay, so that's what we should take note. Okay, so anyway, let's solve the problem using this equation. So we're going to solve the problem using that equation. So let's erase this. So for base, pH is equals to pKa plus the logarithm of your base concentration divided by the conjugate acid. Or for this equation, that is the base is the concentration of our ammonia, And for the acid, that's the concentration of our ammonium chloride, or NH4Cl. So since we are looking at the value of this fraction, we're going to manipulate the equation. Okay, so we're going for the anti-logarithm of this function, because as you can see, this um, this ratio is inside the logarithm function. If your problem requires you to get the ratio, you have to get the anti-logarithm to allow this ratio to be outside of the log function. Okay? The same process that we do when we are getting the concentration of acid using pH. Okay? So to solve for this, we're going to transfer pKa on the other side. That's pH. That's pH minus pKa equals the log of the concentration of ammonia over the concentration of ammonium chloride. Then we're going to get the anti-logarithm of the both sides of the equation. So that means this is 10 raised to pH minus pKa equals to the logarithm of by the way, we already did the anti-log, so we're not going to write the anti. We are not going to write the log function anymore. Okay. So that's the concentration of ammonia over the concentration of ammonium chloride. Okay, so let's solve for this. Okay, so let me rewrite what we have here. Okay, so that is 10 raised to, what is the pH of the solution? pH is 9.00 minus the pKa. Okay, so we don't have pKa. Okay, so let's solve for the pKa first. pKa is the negative log of your Ka. So pKa is equal to negative log of 5.6 times 10 raised to negative 10. So that's 9.25. So 9.25. So the ratio of base over the conjugate acid is 0.562. Okay. So since we are asked, since the problem requires us to solve for the ratio of ammonium chloride over the NH3, what we're going to do is that we're going to get the reciprocal of this number, because we're going to flip the two equation. We are going to flip this. Okay, so in order to flip that equation, we are going to get the reciprocal of this number. Okay, so that means to solve for this, that is just 1 over 10 raised to 9.0 minus 9.25, and that will give us an answer of 1.78. Okay, so this is the ratio that we are looking for. So the ratio of ammonium chloride to ammonia is 1.78.